Okay, then let's get started. Welcome, everyone. It's our monthly invited talk series. It's my great pleasure to introduce this week Tamy Boubekeur from Paris University. Tamy is there a full professor of computer science at Telecom Paris Tech, and he leads the 3D computer graphics group there. His focus is on shape modeling, image synthesis, and interactive systems. Before he was at Telecom Paris Tech, he was at INRIA Bordeaux, and as an invited scientist then at University of British Columbia, Vancouver. He then received a PhD in computer science from the University of Bordeaux in 2007. Then later on moved to Germany, to Berlin, to join as an associate researcher. And in 2008, he went back to Paris to lead the group there at Telecom Paris Tech as associate professor, and he then was later on also promoted to be a full professor there. And Tamy is going to talk about shape proxies, modeling the world's geometry with high level. Okay, Tamy, we're looking forward to the presentation. Now it's your turn. Thank you.
Thank you very much for the intro. And thank you for having me here. I'm not really here, but like I try to act as if I was. So let me start by introducing myself a little bit more so that you see a little bit my background and how the research we conduct is motivated. So as you said, I was at INRIA at first, where I did my PhD, and also part-time at UBC. And at that time, I was really interested in capturing 3D geometry and making graphics applications with that. So I worked a lot on, hierarchical data structures, rendering techniques to display large amounts of data, to edit them, to texture, to deform. And when I moved to Berlin with Mark Alexa, who was a professor over there, I expanded a little bit my field of work, and I started to look more into analysis and topics which are at the boundary between computer vision and computer graphics on several sides, actually. On the capture side, when you design a performance capture system, it's half geometry, half vision work that you have to conduct. But also on the end user side, designing visual search engine, for instance, is something that requires as much computer vision as computer graphics techniques when it comes to 3D objects. Then when I joined Paris Tech in Paris in 2008, I expanded even a bit more, and it became clear that shape analysis was basically at the meeting point between the different things I was interested in. And when I started the group, I started to hire PhD students, some in rendering, some in modeling, some in vision, and they all had in common this 3D spatial analysis aspect in their topics, because this is probably the structuring axis in the group. And since then, I did a bunch of things. Today's talk will be mostly about shape approximation, which is one breed of shape analysis. I also became a professor at Polytechnic, and since 3 years now, a chief scientist at the algorithmic company. That being said, the current group is made of about 12 people, and we're located in Paris. We work on, as I said before, 3 main topics. Modeling, maybe half of the activities are in shape modeling, rendering, and computer vision. Of course, not all computer vision, but the vision aspect, which are the closer to computer graphics. And so today's talk is about shape analysis, and there are various flavors of shape analysis. For us, we see that through the computer science aspect at first. We want to compute things. We want data structure that help supporting shape analysis services. And the system are supposed to mitigate 2 kind of elements. On one side, various amount of data, various models of data, which can describe geometry, appearance, motion, textures on one side. And on the other side, computational models, way of implementing things in real time for interactive system, way of designing scalable pipelines to process huge amounts of data. So one common point to many of our projects is the fact that speed and scalability is not just a feature. It's a fundamental aspect of what we do. And when you design systems which are fast enough and scalable enough, their application spectrum is completely different from just going a little bit faster or a little bit bigger. We are very much interested in interactive systems. So basically for us, shape analysis is at the meeting point between all those aspects where human interact with large systems, large amounts of data, and at the same time, you want the interaction to be clever and harvest interesting mathematical models. So this is the context of this talk, and I go a little deeper and have a look at maybe some of the work we've been doing before that was involving some form of shape analysis, but was mostly focused on processing. So when you process a 3D shape, basically you might want to reproduce the classical primitives of signal processing, but for geometry, filtering, reconstruction, sampling, and so on. And what you end up for is a 3D shape again. And this is an example for classical mesh processing, where you might simplify, subdivide, filter, and so on. Now, shape analysis, on the other hand, might be used to extract parameters that are then used for processing and like drive better the processing pipeline. But they might be used also for editing, changing the shape interactively, for instance. And actually, they may be used for many other things, recognizing a shape, adapting the shape to perceptual elements, to 3D printing, and the various application domain. Actually, there are as many shape analysis framework almost as there are applications. It's usually very application dependent. And the interesting analysis framework, I think, are the ones that can feed many different kinds of applications. Let me give you an example of the previous works we were doing. This particular example is about shape recognition. At that time, we wanted to create like a 3D Google, where the idea was to retrieve 3D objects based on simple input. By simple input, I mean that when you search over the internet for a complicated document, you do not submit to the internet a complicated document as an example. You just give keywords, very coarse, simple, easy to produce description of the complex content you look for. And so we wanted to really have this behavior while searching for 3D objects among large databases. And for us, the visual equivalent of the simple keywords for text-based search was drawings and sketches, actually. Rough sketches, like bad sketches, because most people cannot draw. And including myself, it's hard for me to make a proper drawing with perspective and everything. And so we designed a system so that it would be robust to like the drawing quality an average person can reach. And also that would be reproducing the experience of classical search, which is that when you search over the internet, you get the answer in split second. And having a visual search engine that can map this rough 2D description to a complex 3D mesh description, for instance, was kind of a challenge. And the idea behind that was that at some point we were thinking that assembling virtual scene for VR or AR could be done by just sketching a few objects wherever you wanted to locate them. And then the modeling process would become a sketch, search, and compose process rather than a fully featured sculpting and painting process, like to enable more people to create digital content. So this is an example of the system going live. So basically draw, and while you draw, the system is fast enough so that it refines the queried model and the list of potential 3D objects that looks like what you just drew. One interesting feature is that there is no keyword that you have to enter on top of the drawing. You just draw, and that makes the system kind of international. It doesn't depend on the language you actually speak. Another thing which is interesting is that you don't, like, because it's refining the set of results while you draw, you can actually learn how to draw for better searching while you draw. And that's an important going back and forth between the engine and the user, where the user quickly learns actually how to adjust the drawing so that it gets the kind of objects she wants. Now, this example of shape analysis project was entirely based on statistical analysis, and more specifically the bag of feature framework, which is a standard architecture for searching content. And for this particular architecture, we developed specific descriptors that can like solve this asymmetry problem between a 2D drawing, which is basically black pixel over a white background in 2D, and a 3D mesh, which is a list of unorganized polygons that represent your surface. And really, like the only location where those two objects might be compared is actually in your eye, because this is only through the projection of the mesh in the image plane and then the display of that in your eye that you can actually make a correspondence between those two objects. And that's basically what we studied, like how to select the best point of view on a 3D shape to then sample a signature from it. And then how to get robust signature to this asymmetry problem. On one side, we do have a polygon mesh, on the other side, black and white pixels. Well, it turns out that in computer graphics, there is a field called expressive rendering or non-photorealistic rendering, which had achieved over 15 years a very good result in extracting meaningful lines when you try to convey the sensation of a 3D objects just with black lines over a white background. And that's what we did. We used basically a kind of a learning by synthesis, that would be the term today, but we didn't call it like that back then. And it actually inspired Adobe recently to create their own search engine in some R&D projects. Now, what you see here is how, starting from these 2D drawings, we then ended up having very simple and compact signatures based on the Gabor filter bank, actually, to discriminate locally visual words that could assemble a statistical description of our object and very quickly help us finding in a large collection. Now, this is exploiting statistical analysis for 2D versus 3D search. And like pretty much 2 or 3 years ago, we did something similar, this time purely in 3D, where we wanted to have a selection system where basically when you select something complicated and you took time to actually select a piece of geometry that you're interested in for applying some processing or some editing, we wanted a system that helps you not spend so much time doing the same thing all over the shape. Basically, if you have been selecting a particular feature, just push a slider and all the similar features on your shape are selected as well. That requires a form of live machine learning framework where that kind of system are meaningful only if it's real time. If it takes, let's say, 20 seconds to find out similar features, well, a trained user would just decide to select by hand all the other features. And so we created a system called SeamSelect. You can actually download it. It's open source on the internet, which helps you very quickly select piece of geometry in different form, like patches, components, branches, and then just push a magic expansion slider and recover a similar selection on your shape, even up to symmetry for some of them. So this is 2 examples of statistical analysis, and we use them for various applications: scene composition, scene editing, shape editing, but they come with intrinsic limitation. And one of them is that the abstract model or the compact model you extract from your shape through this statistical analysis can rarely be used as a full substitution to the model itself for a computer graphics application. So it's only through indirect use, like recognition or classification, that such signatures or representations are really useful. And at some point, we wanted to address other kind of problems where really the few numbers that we would retain from complex shape collections would not only be used to retrieve or classify those shapes, but also to actually substitute those shapes in complex application scenarios. Hence, proxies. This is the topic of today. Shape proxies is a different line of research in shape analysis in our group, more related to spatial analysis. Basically, it all came from pushing the well-known surface simplification algorithm to their limits. When you try to simplify a surface mesh, for instance, up to just retaining a few primitives in the end, you quickly see that actually the basic representation of the shape might not be good for such extreme approximation. You also see that the measure of how good a surface area is approximated by its proxy might be revisited, because at some point you move from detail and feature reproduction to volume preservation and like global structure recovery. And when you do that, basically you realize that it's an interesting field of research, because you may have to actually change representations all the time to actually gather a few numbers that do have a spatial embedding, which is still meaningful, even when very compressed. So the goal for us was to be able to then substitute complex objects with simpler ones for a variety of applications in graphics and in vision. Sometimes those proxies, you see one here on the right that we call sphere mesh, which is just a 4-dimensional mesh structure where the vertices are 4-dimensional and the fourth dimension is basically the local thickness of the geometry, and we display them through spheres. This proxy here is used as a high-level controller of the original shape, which means that you use the proxy of a given shape as its own rig for freeform deformation. This is one example. And actually today I will go over two distinct examples on two classes of applications, sphere meshes and bounding proxies. Okay, let me start with sphere meshes. So this project started as a question, basically. How does it work to approximate this one complex shape with just 1,000 primitive? Well, you can use state-of-the-art surface simplification, and it's probably the best thing you could do here. This is here using the quadric edge collapse algorithm, the CASLIM program, if you know it, by Garland and colleague from '97. Still really close to state-of-the-art today, very simple to use, and works pretty much all the time, unless you try to move to very few primitives. And at this point, you realize that with so few numbers to represent your approximation as a surface mesh, actually the simple fact to bound volume of interest with a few triangles in space become too costly. You basically do not have enough numbers to properly reproduce, for instance, a proper topology for our shape here. So what we proposed with sphere mesh was to actually explicitly account for that and recognize that when you go more and more abstract in your shape approximation, at some point, the locally surface representation might become volumetric, and you want it to become volumetric because a sphere, or the Minkowski sum of a sphere along an edge or a triangle, is actually very cheap to represent and can sweep a large part of the volume of interest while staying very close to the original geometry. So this is here an example with 35 spheres, for instance, approximating our input. Now, like using that kind of representation has several advantages. First, it has a form of graceful degradation. So as you'll see later, any surface mesh is actually a sphere mesh for us. Only each sphere is basically a radius 0 sphere. And that really helps bootstrapping the approximation algorithm with something simple. Your input mesh is already an approximation in the form of a sphere mesh. It only doesn't have the right values on its vertices. Second, the more you simplify your shape, actually, the more you might want to actually change its connectivity structure. And what I mean by that is that when you move from an 8-sphere approximation of this capsule here in orange on the left to a 4-sphere approximation, of course, you don't want to preserve the homomorphism that exists between the two surface connectivities. You might want to actually simplify the connectivity to a single sheet. And if you go even more abstract, if you only retain 2 spheres to represent your shape, you might actually want to just keep an edge. Now, what we call here the sphere mesh geometry is the linear interpolation of a set of spheres over a complex made of edges and triangles for most cases, but this also generalized to tetrahedra. Now, sphere meshes basically propose an approximation model which is very fast to compute, starting from a triangle mesh, so that the proxy geometry can be used as a substitution to the mesh, for instance, for visibility applications or physically based simulations at course level, but also as a rig to the original mesh. You can use the model in the middle to actually deform the model on the left. Now, at the core of this is one methodology we try to always use, which is try to model your problem, your approximation problem, through the right metric. So we asked ourselves, okay, locally, the most simple object we can use to approximate a piece of object is probably a sphere. Not that even if you only use sphere, you can always reproduce perfectly flat surfaces, because again, we use linear interpolation of sphere over a complex, which allows reproducing flat regions. And then given a sample on our surface, the question is, like, how does a given sphere in space approximate well this one surface sample? And so we also try to distinguish the inside from the outside. Most interesting proxies are proxies that bound the inside of an object, although for some rendering scenarios, it might make sense to approximate the empty space. But okay, we consider surface samples which do have an orientation, here provided as a normal vector n. And then we design a simple error metric, which is the sum of square distance, which is the square distance, between a plane and a sphere. And this is an oriented distance, which means that it can distinguish between inside and outside. One interesting thing when you start doing that is that you can actually formulate this square distance in space as a quadric, just such as done for classical surface simplification with the quadric error metric. Only we are working with an extra dimension. So here the quadric is not actually a 4x4 matrix, but a 5x5. And its optimizer basically defines, the point on the right here, basically defines an optimal sphere in the least square sense for a set of planar constraints. Again, each planar constraint is basically one sample with one normal vector associated to the surface sample. And the good news is that if you have several constraints, well, the sum of your quadratic is still a quadratic. And so you can still optimize it very easily. And the best fitting sphere is basically, at least a good city sphere, at least, is basically the optimizer of the sum of the quadratic of all our samples. And for a given localized region, that works actually fairly well. So our algorithm is then fairly simple. You start from your mesh. Your mesh is already a sphere mesh, but each vertex is a zero radius sphere. And then for each edge, you basically put in a priority queue the edge, the optimal sphere that would result from the contraction of the edge, and the cost defined from the quadratic I was just mentioning. And then you just pick up the peak of the queue, basically the less disturbing edge. If you remove it, you collapse it based on its, and basically you replace it by the optimal sphere defined by our optimization for this particular edge. Remove the edge, collapse, reinsert the approximating sphere, and iterate. So you're going to basically reinsert the new edges which have been created. This is a priority queue, so all the elements stay ordered based on the cost defined by our quadratic. And we do that for a bunch of edges until we reach the resolution we want. As you can see here, what emerges is something that may be in some region only surface-based, in some other region, sometimes volume-based, and the transition between both is kind of natural, like it's purely based on the thickness of the object. Not also that there is at no point here any volumetrization of the inputs, right? We start from the surface, we never tetrahedrize or voxelize, and somehow the volume emerges from itself. So here are a few examples. The example on the left is a graceful degradation test. Most of the time when you do extreme approximations for complex topology, you cannot reproduce the topology. And so what you want is that at least the geometric embedding stays still. And this is what's happening here. You see we have a cycle, and when there is enough budget, basically the smaller and smaller topological features are reproduced. This is other examples with more natural shapes. I think what's interesting on the right here is that when you go to extreme levels, without prescribing any symmetry in the algorithm by any mean, it actually emerges from the approximation. You get this perfectly symmetric shape with this flat sheet in the middle. And if I give you 12 spheres and ask you to reproduce this one fish, you would probably locate the spheres this way. Same at some point, we just saw an example with 4 spheres that were densely sampled in the input, and which are recovered as single spheres in the end. Last, probably that for junctions and basically characters with arms and legs and that kind of things. This representation is well adapted because it has a tendency to locate the spheres at those junctions. Last example here on the left with this share where basically if you would use, for instance, an alternative to the sphere meshes, skeletal models, you could reproduce part of the chair, but definitely not the seats, because skeletal models only reproduce generalized cylinders, and not all the generalized cylinders, only the one with usually a circular section. In this case, we can reproduce flat surface because, again, this is not only a set of spheres which is approximating the shape. It's the linear interpolation process of spheres over a connectivity. Okay, at that time, we had a fairly efficient, at least, approximation model. For instance, for 100,000 polygons in the input, with that kind of representation, you have basically 100,000 possible level of details by removing the element one by one, and generating and optimizing for this total number of level of details takes less than 1 second on a single CPU. So it's a fairly fast way to get a multi-resolution proxy from pretty much any input in split seconds. And the next step for us was to try to maybe address a slightly more challenging kind of data. So a few years back, as I was mentioning at the beginning, I was working with my colleagues from Vancouver to automatically dynamic mesh, or at least animated mesh, in a purely passive way. What you see here is basically performing a multi-view stereo reconstruction, all automatic and at high precision. Back 10 years ago, that was already possible to get that kind of data, but this data is something you can barely just replay, right? Ideally, you would like to be able to extract something to other object maybe you'd like to simplify the motion or control the motion and the geometry at the same time. And for all those things, you basically need to compute a higher level representation, kind of a superstructure to give an interface to this complex data. So that's what we did. And we designed an extension of our sphere mesh model to account for animated objects. So the example you see here is an animation made of, I don't remember exactly how many frames, but quite a few. And a single sphere mesh is optimized for it. Only each sphere of the sphere mesh has now a trajectory of a time associated to it. So you see here two variants. On the left, one where the radius is fixed and prescribed for an entire sequence for a sphere. On the right, the radius is dynamic and is locally in time adapted to the geometry we try to reproduce. Surprisingly, for most examples, it's actually more interesting to use a fixed radius and try to find the best sphere over time, the best sphere radius over time, and only change over time the trajectory, the position of the sphere, not the radius. Interestingly, actually, moving to animated data was not that complicated, at least in principle. In principle, what we do is that instead of having a single quadric minimization to optimize, we have multiple quadrics over time that assemble themselves in a larger quadric of higher dimension. The dimension depends on the number of frames you have as constraint, but in the end, it's just a single solve again to get your optimized animated sphere for your entire sequence. Okay, so with this representation in hand, there are a few applications you can build fairly quickly. One is it offers a natural multi-resolution behavior in the approximation. You just select one thing, which is basically the number of elements you want in your sphere mesh, and the process will generate a sphere mesh at exactly this resolution and with an as good as possible, according to the metric at least, approximation of the original geometry. So you can use it, for instance, for automatically rigging shapes. So instead of building yourself a skeleton or locating interaction points on your surface or interaction regions or gizmo, you just let the computer compute a sphere mesh at the loading time, and then you navigate the level of detail of the sphere mesh, and you can interact with the sphere mesh at any level by just moving the spheres. And then we basically rig the mesh with the sphere mesh. So we have a scaling that links both, which is automatically computed also in a multi-resolution fashion. And you can use the sphere mesh as a smart interactor somehow for the geometry of your shape. You can also use the sphere mesh as a substitute for physically based simulation, like those collision detections here. I will come on that later. One thing that the sphere mesh does not provide is a kind of a guarantee to be conservative. Somehow the sphere mesh might not be entirely containing its input. For some application, this is a problem that I will talk the next proxy example I give. But for some other application, and when time matters, this is a fairly good approximation. Last, slightly more involved application. So take this performance capture data coming from the Max Planck Institute. Basically extract this motion in a way that you don't have to store all the mesh frames. You just have one mesh with the geometry details you want, and you have an animated sphere mesh that reproduces the motion. So doing that means computing a scaling map that helps linking your sphere mesh, your animated sphere mesh, to the original geometry. And that's what we do, basically. And then through simple linear blend scaling, you reproduce. And the more sphere you use in your approximation, the better the motion reconstruction will be. Okay, so that was one example of proxy, of shape proxy. I'm going to give a second example now, which goes in a slightly different direction, which is called bounding proxies. So bounding proxies still lies in the field of spatial analysis. Only this time we're going to study something which is highly nonlinear. You have a few examples here of what you can do with that kind of framework. Actually, in 2014, we introduced what's called a point morphological framework to process shapes that was already touching a little bit this topic. The framework we study here is called mathematical morphology. And mathematical morphology allows you to change both the geometry and the topology of a shape through a very simple collection of filters that you chain over time. And I go back later on this, but the simplicity of mathematical morphology does not say anything about how complex the topological and geometrical transformation can be on the shape. What you see on the right, for instance, is a topological simplification of the shape through morphology, through actually a closing. And you see here that somehow any piece of geometry that may have an impact on the change in the topology of the shape is affected by the operator. And any piece of geometry which has no impact on the topology change of the shape remains still, including the features. And that's the kind of behavior we wanted when we were thinking about these bounding proxies. So basically proxies designed so that they are conservatively containing the input and are very tight to the input. We wanted to preserve features, but at the same time, we knew that when you go coarse enough, you need to change the topology of your shape. And this is one feature that this framework offers. What you see on the left is another application. Basically, it's this time a shape filtering operator that removes entire shape components based on a thickness measure. And in both examples, there is only one parameter that you specify to the operator, just one parameter. And just by construction, those complex topological transformations are performed by the morphological framework. So back then we designed an analysis framework for morphology, but that was more tuned for point clouds. It's actually called point morphology because we wanted to be able to process raw point clouds and be able to apply morphological analysis on them, for instance, to remove components very quickly. And you see here, when we go by the detail, what those operators look like. Some of those you probably already know, like dilation and erosion. But most interestingly, when you combine them, you get that kind of effect, like a closing when you first dilate and then erode, or an opening when you do the opposite. And those operators are very simple to formulate, sometimes hard to compute, in particular at high resolution. But we basically base the bounding proxy framework on that. So it's a mathematical morphology kind of algorithm that chain two kind of sequences of erosion and sequences of dilation. Dilation is a Minkowski sum of the input geometry, which was called a structuring element. Typically, structuring elements have to be simple, and most of the time having them symmetric makes sense. So they are typically spheres or cubes. And when you compute the Minkowski sum of a shape by a spherical structuring element, for instance, you get this spherical dilation on the top right. If you now use the opposite, the inverse operator, the Minkowski subtraction, you're going to carve the geometry with the structuring element at every point of the input and get this eroded geometry. Now, when you start chaining this operator, you construct more complex shape alterations, like closings at the top, when you apply first dilation, then an erosion, or opening at the bottom. So this is the basic operators we based our work on. And this bounding proxy is basically an algorithm that takes as input a complex mesh and produces as output another mesh, much simpler, much coarser, but which is bounding the inputs and is very tight to the input. So you see in this little video a few examples of those bounding proxies. There are a collection of applications that actually bind the input, such as physical simulation or visibility queries in a 3D engine. There are a few challenges also to actually have good proxies. For instance, when you apply proxies to freeform deformation, they are usually called cages, and they are used to transmit the deformation applied on a simple object onto a more complex object, which is contained within the simple object. This is a standard way of deforming objects, and the key here is that you want to have control on the resolution of your proxy, because in some regions of the space you want more degrees of freedom, in some other you want a more coarse and global control. Physical simulation is also an application that use proxies, mostly because they are very complex simulations, and sometimes having 2 order of magnitude simpler objects might significantly diminish the overall computation. Level of detail in general, for some level of detail technique, you really want to actually keep the overall volume preserved and not carve too much into the geometry. And I was talking about visibility problems. And of course, most of the time with visibility, you want to be conservative. You don't want to remove from your pipeline objects which are actually visible. And so using a simplification of models, which is still bounding, helps you doing so. So the key property you might want for such simplifications or approximation is that your proxy should contain the input. It should be bounding. It should be coarse. the problem is much simpler. If you have a large budget of polygons, it becomes much more complicated when you just have a few polygons, and yet those applications are relevant when you have very coarse proxies, because that's where you usually save computation time. You want them to be tight. A bounding box is, for many applications, not good enough. And you want the geometry to be bounding, but to still be very close to the input. And ideally, of course, you would like the geometry to be adaptive to the geometry of the proxy to be adaptive to the input, so reproducing the main structure and major feature of the input, and also to the user, because for many applications, only the user knows where to put more details, because this is where the interaction will happen at some point. And so we address those problems by construction and up to large resolution with a framework we designed around mathematical morphology. And let's have a closer look to how it works. So starting from an input mesh on the left, what we propose is basically to move to a representation space, which is easier to work with when you do a mathematical morphology, which is 3D voxel grids. We do that in real time on the GPU. And from these voxel grids, we propose a new algorithm that computes, again, in real time, either a symmetric or an asymmetric closing of your shape. You end up with a new voxel grid, which has the geometry of the final proxy you'd like to extract, and you just have to convert it back to mesh format. And the key here is twice. First, you need to voxelize very quickly. Second, you need the closing operation itself to be running in real time. And last, although the meshing might not have to run in real time, it's actually a complex process to re-extract a mesh, it should preserve as much as possible everything you spent so much effort to preserve, in particular the bounding property. Now, the user can interact with the whole system by prescribing a few fields, like the scale fields or the orientation fields, to guide the production of the proxy, although this is optional. Everything can be done automatically. And so one key contribution here was the design of a real-time GPU algorithm for mathematical morphology, and in particular for computing closings that can support what we call the asymmetric closings, which are really interesting for reproducing box-like shapes. So here is an example. So you have an input shape, and because the morphology framework runs in real time, you can actually paint your morphology and prescribe a scale over the shape to refine regions where you would like to have more details and coarsify some others where it's okay to have less polygon and gain a little bit on the computational side. Now, what you just saw was actually a volumetrization that was rendered in real time. We don't extract the final mesh in real time. It's more like a final baking stage here to extract the mesh. But this has an interesting application also in not only in interactive editing, but also in physics simulation. You see here those deformable bodies, which are computed with the proxy for the physics, but keeping the high resolution model for the rendering. And when you do that, of course, you really want to be conservative, because you don't want your piece of geometry to cross each other. This is achieving 100 times faster result. And you see here that it really matters to get a conservative approximation on the left, because the approximation is not conservative. You get your geometry that traverses the input object. And on the right, we preserve this non-penetration property. And here, in this case, about 22 times faster than with the full resolution object. Last, probably that working with this morphological framework was, of course, very interesting for preserving the properties I've been listing at the beginning, but actually you can relax some of the constraints. And even if you don't enforce the bounding condition up to the end, so when you extract the mesh from your morphology grid, you might actually relax part of the algorithm so that it goes faster and generate a mesh which is close to your morphology, your transform morphology, but is not guaranteed to contain it. But even if you do so, it actually has interest for simplifying complex objects. What you see here on the left is a complex object made of about 5,000 components and 2.8 million triangles. And in the middle, it's a state-of-the-art surface simplification algorithm. So of course, those algorithms have no notion of volume. And very quickly, like actually a lot of the components are degenerated to single points and then disappear. When you first regularize your geometry with a simple morphological closing and apply the same simplification algorithm, this is what you get on the right here. And I would bet that for many applications, the simplification on the right is better than the one in the middle. This can be used, so a few more applications. I was talking about constructing cages for approximating shape and then deforming it, actually just such as I showed previously on on the sphere mesh case, your proxy can be used for animating that data as well. What you see here is on the left, a performance capture sequence, in the middle, a proxy, a bounding proxy, which acts as a cage for the model, and on the right, the reconstruction of the deforming object. And so what's on the right is just a single mesh of the input sequence, and this mesh is deformed with the optimized cage, which is automatically fitted at every frame, and that you see in the middle. And then by ruling the resolution of your proxy in the middle, you can rule the approximation of your motion on the right. Okay, so I'm reaching very soon the end of my talk. Before giving a few trends, let me summarize a little bit what I've been just saying. I've been presenting shape proxies, at least two flavors of shape proxy, which can act for many applications as a lightweight substitute for the more and more complex geometry we have to deal with every day in computer graphics. It does not only speed up processing, like physics simulation or visibility, it also offers a kind of a high-level interface to your complex geometry, and they can be used as like a 3D UI for complex objects. The good thing is that they are automatically computed for both examples, so they can basically be computed at multiple resolution at loading time very quickly. The two particular examples I gave was the sphere meshes and the bounding proxies. One is based on progressive graph reduction using a new spherical quadricular metric. The other one is trying to promote the use of morphological framework in computer graphics. I hope more applications of mathematical morphology will appear in graphics in the future. I think there is a lot of possibility with that. One other way to see those proxies is probably also a superstructure to capture data. Data come fully unorganized. Sometimes the first step to organize them is to reconstruct a surface mesh, then to try to rig it and so on. But you can also build those bounding proxies for a bunch of applications directly from your scanned data, and they can already offer services to the end application. And in the end, as I said at the very beginning, it's all about finding the right measure to define how your approximation should fit the input and the right framework to optimize for it. So I hope the morphological aspect of those proxies, at least the bounding proxies, inspire you for your own work. There are really a lot of stuff you can do with mathematical morphology, and in graphics, we do have applications where spatial embedding is key, and this is the central problem. And mathematical morphology is actually giving a very good, simple, and versatile framework for that. Now, beyond shape modeling, so this talk was mostly about 3D modeling application, but you can also find interest in proxies for light transport. If you look at the rendering equation, well, there are some elements which are currently very often approximated with proxies. Basically, the incoming radiance at every point when you work with radiance caching techniques, you can see several of the radiance caching techniques as some form of proxy methods. At the same time, the transport is all driven by the distribution of BRDFs in your scene or BSDF in your scene. And here again, for complex materials and complex relationship between objects, probably that spatial analysis and simplification algorithm can be used. Interestingly as well, it's not that discussed in the academic world, but in the production world, it's discussed a lot. The emissive component of some of your material might actually deserve simplification. Sometimes this emissive component is designed with really complex maps, and to compute the light transport, you might not need actually all this complexity in the emissivity. And finally, there has been a recent trend in plane optic light fields. These are complex objects. The 5D light fields are very complex objects. And approximating visibility relationships or spatial embedding of component of your light fields may actually benefit from bounding proxies. Second, proxy for machine learning in general. I think there is proxy can act as like a good support for laying down robust statistics over complex objects. Maybe not as the sole tool for performing shape analysis or machine learning on shape analysis, but to bootstrap higher level algorithm once you already recognize the global class or global structure on your shape thanks to the proxy. More exciting, maybe the capacity of vectorizing 3D shapes for deep learning is still an open problem. And as you know, you need to vectorize your data to learn from a convolutional network, and doing so, actually, shape approximation may actually be one way of doing it, where you can prescribe actually the resolution at which you want to train and infer later. Another more exotic view of proxies is that's something we're actually thinking about these days, is because those bounding proxies can be seen as shells over the geometry, that they can actually themselves be seen as layers in the neural network that carry functions onto which you train, or that you try to learn. And yeah, moving from 2D grids to 3D surface as layers is something that is already addressed in a bunch of work. And maybe the bounding proxy framework can be used to generate actually those layers. With that, I'd like to thank you for your attention and take a few questions. I'd like to mention all the people who have been working on all those topics. It's not my sole work, of course, it's the work of teams of people. In particular, my students, Stéphane Calderon, Émilie Guy, and Jean-Marc Thierry, which were the first authors of several of the things I've been presenting, and also my collaborators over the world. You can find all the papers and for some of the projects, some source code online on my website. If you have some questions, please go ahead.
Okay, thank you very much. Super interesting stuff. Are there any questions? I think we have a couple of minutes for answering questions.
Yes.
Should I start? Yeah. Okay, my first question is, so I found the sketch-based shape extraction at the beginning very interesting. If you consider the quality of the sketch, okay, how does it work together with the shape approximation? So if someone would sketch something which is very rough, you would get a rough shape. And if someone would add more details, would it also work that your shape approximation is more detailed? Like basically connecting the second part of your talk to the things you've introduced at the beginning.
That would be future work right now. Basically, currently we design the sketch system so that there is a certain parameter in the Gabor filter that helps you being slightly robust to the roughness of your drawing. So that if you do a very rough sketch, what would happen basically would be that you would get a more variability in the set of objects that you get as a query. Using this roughness as a control parameter to actually synthesize more or less precise shape or search for more or less precise shape. That's very interesting. That's not what we did back then, but that could be another way of actually searching 3D shapes, which is that the quality the amount of effort you put into the sketch reflects in the quality of the geometry you find. Yeah,
I also thought about like the erosion and dilution work that you've shown. Like if someone would draw a fat cat or a very thin cat, would you get back to the same shape? To the same shape approximation, right?
Well, the two projects are pretty much decorrelated, but if you try to link them with morphology, it's true that you do have a thickness parameter that helps modeling, how could I say that, like entirely familiar variations of shape, including thickness or fatness, for instance, with very few parameters, basically the size of your support element. Building up a sketch-based search system that accounts for that would be interesting. Actually, using proxies to compute all the signatures for visual search would make sense. That would be for us closing the loop, because that would be going back to shape retrieval through what we have been doing with those proxies. It's a very good idea, actually. Thank you.
Okay, thanks. Yeah, Martin?
I have one question. I've also implemented some mesh simplification algorithms some years ago. I used those algorithms that you showed on your slides, I think from Hoppe from 93 or from 97 and so on. And I've always had the problem that it started to self-intersect actually, and I didn't find a solution for that. Especially if you have a very thin geometry, you start to, because when you do mesh simplification, you start to alter the geometry, and therefore it could happen that you have self-intersections in your geometry. Do you have this problem as well, or did you found?
So that's a very good question, and that's a big problem in practice. If you refer to this particular work I've been showing, we kind of solved the problem because the simplification resolution at which we work is tied to the closing resolution, which means that because we first go through a volumetrization of the shape and then perform the closing at a certain resolution that we aim to reach with the simplification, thus most of the time actually we never encounter the problem actually this solved for this auto intersection problem, because once you're in the volumetric space, in the voxel space, sorry, the closing will basically either delete or merge together the fin structure, and then you mesh that. If you just use a simplification algorithm, like a edge collapse algorithm, yeah, there is no guarantee on the global self-intersection. So far, it's actually a very complicated problem, right? Optimal simplification is NP-hard. Accounting for complex topologies is always a problem, in particular when you have thin structure. Now, from what I know from the industry, because of course simplification is used a lot also in the industry, going through voxelization of your inputs is actually the method many systems use. They don't directly work on the mesh that is on the input. They first volumetrize it with voxel grid, for instance, and then they work on that so that they can kind of track or prevent topological problem a little bit better.
Okay, further questions?
Yeah,
David?
I would have one more related to your sphere meshes. So you showed this example where you had the skeleton of the hand, basically, and you used it for animation. And there, the joints, or there your spheres, were basically on the joints of the fingers. Is this always the case, or how does this happen? And one question related to this is, could you maybe change positions of your spheres so that it would be easier to animate some objects? You use that for the application of animation?
Okay, so on the first question, it turns out that for static objects, when you have a conic region, you will have it will be easier to fit a sphere there than on the cylinder region. You will have basically more faces that vote for having this sphere exactly there. So for the tip of the finger, for instance, yes, most of the time it actually ends up near to it. And if you want to emphasize that, we have in the paper a curvature-driven modification of the algorithm that helps even enforcing having spheres at those extremities. Now for joints, it's a little bit out of the actual morphology of those shapes. Very often when you have joint, it reflects in the geometry, right? If you have an arm, unless really the character has a perfectly straight arm, it's slightly bended, and then all of a sudden the sphere will be localized here through the process because more polygons will vote for having this sphere there. This is a side effect. You can build artificial examples where, of course, the sphere will not end up on the elbow, for instance, if you have a very straight elbow. That, however, emerges from the animation. So if you have animated data, then, of course, the spheres will be perfectly located in the joints, because this is probably the location that, through the edge collapse process, gives the less error in the approximation. Okay, and so far, can you remind me your second question, please?
The second question was, but you answered that already, kind of, if you could add a constraint where your spheres should be, or that you could reposition some of your spheres for this.
Okay, so we have indirect constraints right now, where you can emphasize through curvature, for instance, that in highly curvy regions you do want spheres. We don't have any explicit way of doing it, but it would be trivial to integrate, like an interface where you click somewhere and that enforces a sphere to be there, or that multiply the chance of having a sphere there by a certain factor. That would be fairly easy. All because this is not a global, there is no global system to solve, or there is no global energy formalized at any point. It's always a graph reduction that we do in these sphere mesh algorithms.
Okay, great. Further questions? If not, then let's thank Tamy again. Here. Oliver is also back just in time to say bye and hi, probably at the same time.
Hi, Oliver.
I'm very sorry I had a short notice faculty meeting.
No problem. I hope my talk was clear. That's actually the first time I give a talk at a distance like that.
Oh, it was perfect. And Oliver can watch the recording then.
Yeah.
Okay.
And yeah, thanks again. Our next talk will be in May, given by Eric Reinhardt from Technicolor. He's working on high dynamic range imaging and also visual perception. The date is not final yet, but we will send out an email in time. So thanks again for coming, Tamy. Have a great rest of the day, and bye bye.
Okay.
Bye.
Bye bye.